morning, Engineering 2. Let's talk about feeds. Come over here. What is a feeds? What do I know with feeds? And I forgot to bring my doohickey. I usually have a little assembly. I want to assume you guys seen it before. It looks something like this. Usually I bring it, I forgot it. It looks something like this. Like I believe I have like 2 rows, something like this here. And it looks something like this. You've seen it before. It's a piece of metal that I use it to bend things. I believe I also have a pin somewhere. Maybe a pin here. And another pin somewhere there. And again, I forgot it. Sorry, guys. What I'm trying to say here is we want to focus on one thing. Remember, we got G, D, and T. What I want to focus today is on the D. In Intake 34, which is the next one, we'll focus a lot on the G, which again is the geometric tolerance. For now, I just have told you, hey, put a little plus and minus. That plus and minus is going to take care of a couple of things. It's going to take care of the surface inherently. If you need a different type of surface, you can go and put the little check mark. It also will have the overall size, right? And it also will take care of things that fit with each other. So that's where the fits come about. The numbers that are otherwise, you guys seen this before. Unless in your notes, unless otherwise specified, you're going to put plus minus 50 thousandths, and things that require a center, something that is only otherwise, again, this is in your notes, right? Unless otherwise specified, use this. If I specify it somewhere else, it's because it has a special function. And one of the functions that is going to require us to change this guy is to be how things fit with each other. Okay. So that is pretty much the lecture of today. So now what do I mean fit with each other? How they meet? A part never lives by itself. And we live in an assembly. Let's say the assembly will look like that. Right? This part will live in an assembly. And then things will start meeting with each other. The lecture of today is how do I determine the size of this part such that when it goes inside of my assembly, it will function the way that I want it to function. How things mate with each other. Pretty much. That's pretty much what's today. Let's start the lecture. So fits. It refers to the amount of tightness or looseness between the mating parts. There are 3 types of fits. Clearance, interference, and transition fits. Let's take care of the first one. Clearance fits. The clearance fit is one in which there is a space remaining after mating parts have been assembled. Though I have a clearance fit somewhere that I can show you. There we go. Here, let me show you this clearance fit. Go back. Okay, so you see here, this is my marker. Okay, and I'm gonna come over here and I'm going to put my pin. You will notice that pin can rotate. It's nice and loose. There is a little wiggle room, and then eventually it has a little interference right at the end. You push it, and now it doesn't move anymore, right? So that's kind of like an interference at the end, but everywhere before it is nice and loose. This is what we call it a clearance fit, a looseness fit. How do I ensure that if I were to make 1,000 parts, they will all fit the same way? For this, we gotta go back to the basics, which I'm going to make a basic here, and I'm gonna make let's make a part that is wiggly. Let's make it a wiggly part. This is gonna be my pin, okay? This is my pin, and again, I'm exaggerating the size of the wiggliness of the pin, so it makes a little sense on things that are going to be mating with each other. So again, here I have my endpoint, and here we have my axis on the pin. This pin is going to be mating in a hole. So we'll make my hole. I'm going to put a hole over here, over there. That is the part, and somewhere inside of it, I will have a hole like this, right? In fact, let's make the hole 3-dimensionally, right? going to grab that hole and I'm going to make it a little bit crooked. I don't know how to make it crooked. I'm going to make it a bunch of hidden lines, crookedness, right? Because it's in 3D, right? Hopefully that makes sense. This is the front of the hole, right? This guy here is the back of the hole. Maybe put a little more hidden lines. And this crickety guy has to fit in this crickety hole that is not perfect. That guy is not perfect, but I know a couple of things about this. I know that when I told the manufacturer to go and make it, when I make my pin, I'm going to draw it like this. I'm going to draw it like this. And again, this is my side view. That's my pin. When I go and I made the size of that pin, I told it, go and make my hole, let's say 1.000, right? But also, if I want to have things that are going to be mating with each other, I want to give them a little plus and minus. The little plus and minus is going to be an important plus and minus. Let's say that I make it plus 0.03 minus 0.002. That could be any number, right? What is this telling me? It's telling me how bigger it can get and how smaller it can get. Now, you guys have seen this before. This we call it maximum material condition or least material condition. Sometimes we call it the M, sometimes we call it the L. The biggest material that I can have, the least material that I can have. So for example, this is, if I were to add those two, will give me my maximum material condition, the more material I can have. If I were to grab those two, this guy, and again 1 minus 0.002 will give me the least material condition. The smallest that I can get, right? Let's write those down. 1.003 and 0.998, right? And again, this guy will be my MMC, this guy will be my LMC. In reality, my part gets to live everywhere within this size, right? So I am going to draw an imaginary boundary that would encompass how that guy can grow. And actually, in 3-dimensional, let me see if I can go draw it in 3-dimensional. Let me make it bluish. I'm going to make it 3D. I'm going to make it 3-dimensionally. Something like that, right? Guess where my part could live. You see it? My part can live anywhere within this tolerance. So again, my part could be anything. And to make it mathematically easier to calculate and understand, I usually like to graph and make the bottom perfect. So pretty much I graph the hole and I shift it sideways so all the tolerances get to be on the top. So it will look something like this. I will make it perfect on the bottom, and then I make it wiggly, right? And then I grab my tolerance zone, and I push everything on the top. So I can grab that whole thing, right? Right now I have a little bit on the top and a little bit on the bottom. And again, I am putting this guy and that guy, everything on the top, so it will look like this. And again, it helps because it makes it mathematically easier to understand, especially on the math, right? So what I can do is, my pin has a leeway. It can be as small as 0.98 and as high as 1.003. I want to ensure that doesn't matter what I do, there will always be some leeway. So when I fix things together with a hole, this guy will always be the case. This guy will always be the case. So how do I do it? Well, I'm going to make a hole here and put it right there. I'm going to go to the bottom, which is going to become like the where I would go and make in terms of the bottom again. Grab that pin and I stick in there. Then I'm going to grab the biggest I can get, and I'm just going to dot it, right? That will happen if it will be the biggest it could be, right? Smallest I can get, the biggest I can get. I'm going to grab that and I'm going to give it a little bit more, right? So you say I'm going to start my hole right here. You guys see it? I'm going to grab this one and I'm going to give it a name. And again, my hole doesn't exist there, but I'm going to say this guy, this little distance where my hole starts to originate, I'm going to call it allowance. Allowance. Okay. Now my hole now, because I have, again, this is the biggest I can get, right? I grab the pin and I stick it inside of it. And because I have a little bit of allowance, it will always fit. Now, my hole also needs to have a tolerance. It needs to have a plus and minus. Okay, so what I'm gonna do, I'm gonna give it the tolerance by making the hole bigger. See? So that means that when my hole gets to be manufactured, it's gonna be, well, bigger than what this guy is already is, by a little bit more. And then if I'm gonna give it a tolerance, I'm gonna give it this way, so I continue getting bigger, and my hole will always be bigger than my pin. Right? So let's say that I'm gonna give it, I don't know, maybe 0.002 for the allowance. That means that if I were to go and I were to grab that pin and insert it, and push it inside of it, there will be a little gap, right? And the smallest that my hole could be will be the biggest this guy can be, plus whatever extra I gave it, which is 0.003, 0.002. So in this case, will be 1.003 plus 0.002, which will be 1.005. Now, remember I told you, I want to ensure that the pin will fit in the hole, and if I gotta give it a tolerance, we'll just write 1.005. If I were to give it a tolerance, I gotta make my hole even bigger, right? Because I wanna still keep that 0.002 in the middle. So I don't know, let's give it, I don't know how much I wanna give it the tolerance. Let's say I'm gonna give it the tolerance, I don't know. I'm gonna give it maybe 5,000 of an inch, 0.005. That means that the biggest that my hole could be will be 1.010. Right? 1.005 plus 0.005 will give me 1.010. Right? Now, what's happening right now? I am grabbing that pin. I'm able to put it inside of the hole. It has a little bit of wiggle room. I can determine the diameter of the smallest hole, and I give it a little bit of tolerance to allow it to have some wiggle room for the manufacturer, and allows me to determine the maximum size of the hole. This type of condition, by always having a positive allowance, will allow me to always have a clearance conditions. It might hold my pin get to deviate in terms of the size. Even at the worst case condition, if the pin were to be at 1.003, it will always fit in my hole, because, I mean, you guys can see it, right? I can grab the hole and I can slide it in, and it will fit. This is what we call it. This is what we call a clearance condition. Now, mathematically, we can also do something like this. And again, the whole idea is to make the hole bigger, even at the worst case condition of that one, given a little bit of wiggle room, give it a wiggle room, which we call the allowance, and allow for the tolerance, and then give it the size, right, based on whatever you allowed, and whatever your tolerance you want to give extra. Pretty much it. Okay, mathematically, how can I do that? Let's say that I want to do something mathematically. You can also do a formula for this. Mathematically, this is how you do it. Actually, I have a cheat sheet for this. Let's go show you the cheat sheet. I think it should be on your cheat sheet somewhere. I'm gonna go find it. And I am going to come over here and look for 11. And somewhere I created a cheat sheet which I'm gonna go open. Okay, so this is the cheat sheet. We are looking at calculations. System is not link. Calculations. What is the calculations? This one is the one that I want to do. Let me rotate it. And again, you guys have it black and white. If for whatever reason you want to have it printed color, you guys are welcome to reprint it in color. You should have this in PDF in your Dropbox. The one that I am doing right now, it is when I have a shaft or a pin that is going to go into a hole. The shaft has its own tolerance zone. The pin has its own tolerance zone. Doesn't matter what I do, I will always have a little wiggle room. We call that wiggle room the allowance. And the allowance stands for the tightest fit. Let's see, what does it mean? Let's say that I have a pin that needs to go into the hole. We'll put it. Okay, so as you guys could see, it can go inside easily, right? That would be the biggest the hole the pin can get. Now, my hole is going to start, let's put something on the bottom, my hole. The worst case condition, it could be, again, remember, my hole can grow, right? It can grow and it has to live within this region. This guy will be the best condition, right? Because the hole will be the biggest. And then this guy will be the worst case condition when the hole is the smallest. When the hole is the smallest, right? If there is a positive allowance and the shaft is the biggest, I will have what we call it the tightest fit. Now let's take a look at the tolerance zone. Just the colors by themselves. See this region that I made red? And I made another region somewhere here blue. Just looking at the region of the tolerance. This is the red, this is the blue. This is the red, this is the blue. The red one is on top of the blue one. Just by looking at the tolerance alone, you can determine that it's a clearance fit. I mean, again, I'm going to hope that you guys will see that doesn't matter. Let me see if I can chop. I can clip it. That way I can move it. That's it. No. Try again. Sometimes it allows me to clip it. There we go. Let's try again. There we go. Okay, so if I were to grab my pin, which is right now, and I were to put it inside of it, it will always fit. It doesn't matter in fact why, because even at the worst case condition, it will always fit. If I were to look at just the tolerance themselves, the red one is above the blue one, right? Which is what you guys see here. Just looking at the tolerance on alone. So what is the tightest fit? What is what we call it the allowance? This is what you guys see here, allowance. What is the maximum clearance? Well, the maximum clearance is when I'm looking at the best mating condition, which would be when my shaft is the smallest and my hole is the biggest, right? Because I will have the best mating condition. And this is what you guys notice if I were to say, okay, what is that? Well, it will be from here to there, right? That will be the maximum amount of leeway that you will have. This is what you guys will see here, and that's we call that the maximum clearance, or we also call it the loosest fit. Looking at the tolerance on alone by themselves, and then you guys can see how I measure from the top of the red to the bottom of the blue. It's pretty much what you guys see here, right? Now, mathematically, the shaft MMC will be the more material that I have. What is the shaft MMC? The big pin. Big pin. Big pin. Thank you, Sabrina. The hole. The hole is the small hole. Remember, the maximum condition of a hole is when I have the most material, which is when I have a smaller hole. If I were to have a small hole and a big pin, and even after I got the big pin, I can put it into the small hole, that means I will have clearance fit. The way you can do it mathematically is by going into this, and again, this guy is the MMC. Go ahead and move my camera. Let's put some other. Put out something. Focus. Focus, guy. Sometimes it takes a little bit to focus. So there. Let me change the resolution. Sometimes I need to flip it and then change it back. Let's put it there. There we go. Remember, this is the MMC, the LMC for the pin. This is the MMC for the hole and the LMC for the hole. And if I want to know if it's gonna mate, all I have to do is compare the MMCs. So, for example, is it gonna be a clearance? All you have to do, okay. So let's say the MMC of the hole and the MMC of the pin. You compare both of them. If the MMC of the hole is bigger than MMC of the pin, it will always guarantee that you will have a clearance condition. The MMC of the hole, 1.005. The MMC of the pin, 1.003. Is the MMC of the the MMC of the hole bigger than the MMC of the pin? Yes, this guy is bigger. Which means yes, doesn't matter what, this is the condition. You will always have a clearance condition because there is a little wiggle room. Mathematically, you can also figure out if it's going to be a clearance condition just by looking at which one is MMCs, right? And see and ensure that this guy is always bigger than that guy. Hopefully that makes sense. Okay, that's what you guys see there. Now, in terms of the lecture, this is what pretty much I try to tell you, right? A clearance fit is one which there is a space remaining after the main parts have been assembled. It is used for moving parts, rotating or sliding, and for parts which must assemble easily. Yes. And again, what you guys see here is the mathematics to be able to find the allowance. And if you guys come over here to the cheat sheet that I gave you, what is allowance? Allowance is this little distance. I can go and I could do it with the sketch that I did, or this distance, right? Another mathematically way of doing it is by looking at the MMCs and the LMCs. If you want to go and do and take the difference between the MMCs, you will find the allowance, which is what you guys see here. The difference between the MMCs will have the allowance. You can also, for the loosest fit, you can do the difference of LMCs, which I should have somewhere here. Loosest fit or clearance is the difference of LMCs. And why does it work? Right. The tightest condition is when I'm looking at the MMCs. Again, remember, MMCs is this one, right? When my pin is the smallest and when my pin is the biggest and my hole is the smallest. The MMCs are where the pin is the biggest, my hole is the smallest, is the worst mating condition. So MMCs are worst mating conditions. If I want to know the worst mating conditions, I look at the MMCs. Subtract them both will give me the worst case condition allowance, which is again is the tightest fit. Now, if I want to look at the best condition for assembly, I'm looking at the LMCs. When my pin is the biggest and my shaft is the smallest, the region where this guy will be really, really small, the pin will be really small, and the shaft will be really big, that will give me the best mating condition. And I could do it by just looking at this guy, the little distance. That guy will call it clearance. And again, it's also the best fitting condition. Sometimes also you would call it the maximum clearance. Okay, let's call it the loosest fit. Right. So mathematically, you can also go and subtract one minus the other, and then will give you your clearance. And that's what you guys see here. Right? This is a clearance over here. The LMCs will give you the best loosest condition, and it will give you a value, right? That means that's the wiggle room you have. That's pretty much what it is. Once you go and you put it at the worst case condition, the wiggle room that will always be guaranteed for your part to assemble will be this one. And at the best condition, the wiggle room will be that one. That's pretty much what it means. Let's take a look at the next one. Clearance condition. Interference, what does it mean? Okay, let me see if I can draw it. Nothing like drawing. I'm gonna grab that one. I'm gonna get a new sheet. I'm gonna put it right on top of it. Okay. In same concept, I have a pin, and it's gonna go into a hole. Right, the pin goes into a hole. So how do I guarantee that I will always have an interference condition? Right. So I'm gonna grab my pin. I'm gonna have my pin. I'm gonna draw it like this. Again, remember it has a leeway. Now, because I want to ensure that it will always interfere, I am going to grab my hole and I am going to make it smaller. Let's use that as the bottom, right? I'm going to make it smaller. So even at the best condition, the best condition when my pin is the smallest, it will not fit into the hole, right? And then what else am I going to do? I got to give it a leeway, right? So I'm going to give it a leeway, and my tolerance zone will be here. Now, it doesn't matter what I do. This guy, if I were to meet over here, will be interfering. And then you are telling me, Professor Scalona, so how do I make a fit now? If that guy has to go there, and it needs to have an interference. By the way, this one, the little fit that you see here, this is not an interference fit. This one, the last fit, I remember I got the sharp fit before. This is clearance. This guy I'm able to disassemble. This is actually a transition fit. This one, the end one, that you cannot move it, but if you were to push hard, it will come off. This is the next type of fit that I'm going to do. But if I couldn't move it, will be an interference fit. Interference fit is I'm going to have to mess with the temperatures such that when it fits, it will never be able to come off. And if I take it off, the thing is going to fail. I'm going to damage the part. How do I do that? Very easy. If I want to make this mate and I don't want it to come apart, I'm going to make this guy hot. I'm going to raise his temperature. As it raises this temperature, this hole is going to grow. Yeah, right? At this point of time, I grab my pin, put it inside of it. Again, my pin is not, I did not put it hot, right? Still room temperature. I'm going to make that guy grow. I'm going to grab the pin. I'm going to put it inside of it. And if I need a hammer, I'm going to hammer it in. It's going to go inside of it. At that point of time, I'm going to then cool this guy off. And as it's cooling off, it's going to start shrinking. And believe me, that guy, once this guy has cooled off, it will never come off. It's going to be as solid as a welded connection. That's how you do it. Okay, how do I do? By the way, all of this we'll talk about how we determine the allowance and the clearance, the tolerance. We'll talk about it next time. For now, we just gotta understand what is happening. Okay, so let's say what is the worst case mating condition? Well, the worst mating condition is when my shaft is the biggest and my hole is the smallest, right? It will be super hard for this guy to go inside of it. This guy here, that little distance, is what we call it allowance, as I previously told you. However, I'm not allowing anything. This is I'm not allowing anything, and again, it's still the tightest fit, because I'm not allowing anything. In fact, my pin is so big, bigger than my hole. If I were to do this mathematically, I would have a negative allowance. I would do it mathematically with negative, which again is the tightest fit. Now, if I were to do the best condition, that will be meaning that my hole will get the biggest it can get, and my shaft will get the smallest it can get. That's the best condition that I could have in terms of assembly. This little distance here, it is the the best condition, right? Let's call it the loosest fit. Loosest fit. And if you guys remember, the loosest fit is also sometimes called clearance. But guess what? This is a negative clearance. Why is it negative? Because I'm not clearing anything. Mathematically, I will put a little negative. Remember, allowance, the worst case mating condition. Clearance is the best mating condition. But even you guys can see it. Even at the best condition, I still will not fit. Let's make the pin the smallest and the hole the biggest I can get. My pin is so big that it will not go in. Again, the only way that I can make it work is by making the part hot, make it expand, and then grab this guy and stick it inside of it. Okay. Remember, this guy is what the tolerance is for the hole. And then this guy is what the tolerance is for the shaft. I can do this mathematically as well. I drew it, as you guys could see. I drew it and I was able to find the allowance and the clearance just by looking at the dimension, the distance between them. But I can also do it mathematically. I can go and I can say that this guy will be my MMC for my hole and my LMC for my hole. Least material condition, maximum material condition. Remember, MMC, LMC. For my shaft, this guy will be my MMC and this guy LMC, right? Maximum material condition for the pin, least material condition for the pin. Mathematically, I can find the allowance by taking the change on the MMCs. Remember, because it's the tightest condition, is when I have the biggest shaft, the smallest hole. Subtract -1 minus the other. Remember that your allowance will have to be negative, right? Because you cannot do it, right? It's kind of like saying, I want to take away 1, and I'm going to take away, from 1, I'm going to take away 2. Well, I will always get a negative number, right? You can also do the clearance, right, which will be the loosest fit. And that, again, in this case, will be the change in the LMCs. Grab that number, take away from that number. And you will always get a negative number because the LMC, it will be always smaller than the LMC over there. You will always have a negative clearance. So I can assure that doesn't matter what size my pin is, anywhere within this region, will always be bigger than the hole that is over here. Doesn't matter what size it is. we call that interference, which is what you guys see here. Interference fit is the type of fits that occurs when there is a negative allowance, and in other words, when the shaft is larger than the collar with which a mast mate. Doesn't matter what I do, I will always interfere. And again, remember that the allowance is the title fit change in MMCs, and the clearance is the change in LMCs. Transition fit. I think that's where we want to leave it. Transition fit is where I have a transition between it. That means I am going to be able to assemble things, and they are not going to be clearance. They are not going to be interference. They are going to be somewhere in the middle. Where is somewhere in the middle? This is somewhere in the middle. See it? I can go, this is clear, it's wiggly, and then I put it inside of it. Now it is hard to move, right? In fact, it doesn't rotate anymore. But if I were to pull with a little bit of force, it will come off. That is what we call it a transition fit. Okay. We're gonna learn where do we get the numbers for all this. Most likely next week. We can find out exactly how to put this tolerance so it behaves the way we want. By the way, in your cheat sheet, if you guys want to do your interference, is also there. Let me see if I can find it. That's your interference fit. Right, the shaft is always bigger. It's bigger than the hole. If you were to do it with the shaft and the hole tolerances, you can find the minimum interference or the maximum interference. And again, you can also do it mathematically, right? Okay, what is a transition fit? A transition fit is when I have a hole, and this is my hole on the right side, and this one is my shaft. And if I were to look at the tolerance zones, the tolerance zone and a tolerance zone, there will be a variation. A variation, actually, no, let's call it not a variation, an overlap with the tolerance zones. What do I mean an overlap? If I were to grab that tolerance zone, I can copy it. If I can grab that tolerance zone, and I were to grab it from where it is, and I were to drag it to the right, it would overlap. This is called the overlap. And what would that mean? It means that when I have a transition, I actually have a combination of things. I don't really have an interference. I don't really have a clearance. I have something in between. Where mathematically, sometimes you will have an interference, sometimes you will have a clearance. We call this guy a push fit. Push fit is I push and it fits, and I pull and it fits, like my Sharpie. So let's say mathematically, this means that I will have both of them, a clearance and interference. Let's say that I want to make my, let's say, when do I have an interference? Then we have a range of interferences. But let's say, let's do the worst case condition. If I were to make my hole the smallest, right? And I were to make actually in this case I have a bunch of interference. If I were to make either my shaft the smallest or the shaft the biggest, or anything anywhere in between it, if I made my shaft my hole small, this guy will not fit. I want to hope that you guys could see it. You can grab this guy, you can grab this guy, try to put it inside of it. My hole is the smallest it could be, it will not fit. However, I can also have clearance conditions. If I were to look at this condition where I have my hole is the biggest, right? And I were to look at the condition where my shaft is the smallest, right? That shaft will fit. In fact, there will be a little bit of wiggle room right there, right? And in fact, if my shaft continue growing and 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 growing, it will still fit, in theory, until I get exactly the same size as my hole, right? When the shaft continue growing, when it's the same, then it will not fit. But as long as it's below it, I have a region that will fit. So a transitional fit is when I have both of them. I have a interference fit and I have a clearance fit. Both of them at the same time. And my tolerance zone, looking at them both, these are different examples, right? Looking at them both, my tolerance zone will interfere, kind of like they overlap with each other. When I have that, I actually have ranges of clearances, ranges of interferences. This type of fit we call a transition fit. Next time we meet, we'll do we'll talk about where do you get the numbers? How do you have a by the way, we have flavors. We have flavors on how we make things fit with each other. Maybe I want to have a lot of clearance, maybe I have a little clearance. How do I do that? Okay. Let me stop the share. I think that's how we're gonna leave it for today. I'm gonna go and pause this. I'm gonna